So we have the first speaker who will be Torben Moos, and he will talk about prime field masking in hardware and its soundness against low noise side channel attacks.
Okay, thank you very much for the nice introduction. So this is a joint work with my colleagues Gaëtan, Loïc, Charles, and FX from the crypto group at UC Leuven in Belgium, and Gaëtan is in Graz in Austria at the moment. So the first part of the talk, I will try to argue why and maybe convince you why prime field masking is something that is interesting for security, for side channel security, and why is something that we want to have. And then in the second part, I will talk about our contribution towards making that feasible, towards making that efficient. And I will start with why do we even want masking? So like the typical assumption that we have with side channel attacks is that adversaries can make imprecise observations of what's going on inside the cryptographic implementation, of what's going on inside the chip. And masking can be used to amplify this imprecision. So let's say we have only one share. So it's directly the intermediate value that we target, and we know the Hamming weight of that share is either 0 or 1. We have a probability distribution, and we can already exclude some values that it will be or will not be. Now, if we have masking, and about my second share, for example, I'm pretty sure that the Hamming weight is 1. The resulting probability distribution on the intermediate values that we are trying to target is already like a bit more evened out. So it's closer to uniform distribution. And this increases if I add more and more shares. So for the third share, I assume the Hamming weight is 2 or 3. And then my knowledge about the secret decreases progressively with the number of shares. That's usually what we want, so that we spend something, more shares is more expensive, and that we also get higher security for that price that we pay. Now, does it always work? And the answer is unfortunately no. Here is an example based on Hamming weight leakages on the left side in green for Boolean masking, so in the field f2 to the 7. And on the right side, we have a prime field, which is f2 to the 7 minus 1, which is 127, a prime number. And on the left side, we can see when we're looking at the mutual information between the Hamming weight of all the shares and the actual secret, plotted over the noise variance sigma squared, we see that for very low noise levels, we actually have no advantage by increasing the number of shares. So on the very left of the green figure, we see that for all shares, there is no difference. In this talk, D will be the number of shares. So we have for D equals 2 up to D equals 6, this information theoretic plot. And on the right side, you can see that once you operate in a prime order field, you actually get amplification even with super low noise. And we see that we have equidistant steps between the different curves for the different numbers of shares. And it is on a logarithmic plot, so we have exponential security here. We have a similar scenario when we consider bit leakage. So we leak 1 bit of each share, in this case, the LSB, so the least significant bit of each share. For Boolean masking, we have no increase with low noise. For prime field masking, we have increase with low noise. Now, let's look at a more concrete example. So we get noise-free Hamming weight observations of 2 shares. And my Hamming weight of A0 is 2, and my Hamming weight of A1 is 1. If my combination function is A equals A0 X or A1, then we get the probability distribution on the left for A. And if my combination function is A0 plus A1 mod 7, which is like the addition in the field f2 to the 3 minus 1, then we get the probability distribution on the right. What we can see is that on the left, we can already exclude like a couple of values, like 0, 3, 5, 6. And on the right side, we have like probabilities for each of them, so we cannot exclude any more at that point. Now, if we increase the number of shares, so we have another share A2, the Hamming weight of that is 2. The left distribution doesn't change a lot, so we still have like the same values that can be represented. and the right distribution is more and more approaching a uniform distribution. And now we can increase the number of shares even more to 4 shares and to 5 shares and even to 6 shares. And what we see on the left side, there's basically no change. So we have like lots of leakages of the intermediate value of the intermediate shares, and it helps us to get a good picture of the value of A. And the increase of the shares doesn't help a lot, while on the right side, we actually get closer and closer to a uniform distribution. A uniform distribution for the probability of A would mean that we don't learn anything because all values are equally probable. Now, why does it happen for Boolean masking? Because the parity of the Hamming weights hits a subgroup of F2 to the n. So if my Hamming weight is even, my other Hamming weight is odd, and my other Hamming weight is odd, I don't have any increase. So I don't have security amplification. I don't have uncertainty amplification, which is a problem. Now for bit leakages, so again, LSB leakages, we have the same scenario. So on the left side, the LSB of A0 is 0, as the LSB of A1 is 1. We get the distribution on the left side and on the right side for the prime field. And we can see that on the right side, we have more values represented. So it's like a bit more ambiguous which value A really has. And this only increases when I increase the number of shares up to 6. Here again, the parity of the LSBs hits a subgroup of F2 to the n, which is problematic because directly from the LSBs of all shares, we know the LSB of the secret. So this is why prime field masking actually has an advantage. And these low noise attacks, they become more and more common because advanced multivariate SCA attacks, they try to extract and combine as much information in each trace about the targeted intermediate value as we can to reduce the effective noise level, to get like a very good estimation on the intermediate values that we want to target. And if I then have a good algebraic compatibility between my leakage function and my field operation, that can become a problem when the noise level is too low. This is when I hit these subgroups. Parallelism doesn't help in this scenario because if I add up all the Hamming weights or I add up all the LSBs and I see them as a sum, I still see the parities. So in this noise-free scenario, it doesn't help at all. And what we know is that whenever I have 1 bit or more of leakage per share, then masking in binary fields may not guarantee security amplification. So in all these scenarios, we actually need to make sure that we have enough noise. Now, if I take FP with P a prime, there are no non-trivial subgroups of that field, and we have no algebraic compatibility between leakage function and field arithmetic. So amplification is actually guaranteed for any non-injective leakage model. That means any leakage model that doesn't give us already all the information about the intermediate value, in which case masking doesn't help anyway, leads to security amplification, which is like a really cool feature. So how can we use this knowledge to effectively protect crypto implementations? And what we ideally need for that is like crypto implementations that work in implementation-friendly prime fields, such as, for example, Mersenne prime fields, like in my previous example. So a Mersenne prime is a prime of the form 2 to the n minus 1, and that only use simple field arithmetic. So additive masking is pretty cool. Since we didn't have like the perfect primitive, especially no block cipher, which is what we typically consider in these scenarios, at Eurocrypt this year, we introduced a toy cipher. So just as a first example to study the effects of prime field masking. And it's like an adaptation of the AES to a prime field, and we chose 2 to the 7 minus 1 as the Mersenne prime field of choice, because it's like the closest Mersenne prime to the Galois field 2 to the 8 that AES is usually using. We have the same 4 times 4 state. The S box is a small power map. in FP. So in fact, it's given at the bottom, it's x to the 5 and plus 2 for some affine mapping, modulo P. So this one is not directly a mapping of the inverse that the AES S-box uses, but we wanted to compare two strong cryptographic S-boxes in both fields to get a comparison later. However, there is a disclaimer, this S-box doesn't have a very efficient inverse, so take the comparison at the end with a grain of salt. And at the Eurocrypt paper, we built like a complete cipher and analyzed the security, and we get like a similar number of rounds to achieve a similar security level. Now there's one problem. If I want to implement the power map, a mass power map securely, in hardware, I would need some robust probing, secure and composable multiplications and squarings. Now, multiplications, we know gadgets, many of them, and some of them are even field agnostic, like ISW, DOM INDEP, and HPC1. The squaring operation, on the other hand, because it's linear in binary fields, and Boolean masking is the most popular masking scheme, it has not received much attention because you don't need a gadget for that with Boolean masking. You just square each share individually and you are done with the linear operation. But here, in prime fields, we actually need a gadget for that. And of course, you can use a multiplication gadget. However, we found that it's not particularly efficient, so we developed new gadgets in that regard. So this is a glitch-robust 1-piney squaring gadget. It's usable for any field, but as I said, it's mostly useful for prime fields. And for binary fields, you wouldn't want to use that. And what we can see is that for 2 shares, it basically uses 2 partial multiplications. Let me try if that works. This one here and this one here, while like an ISW or DOM INDEP multiplication would need at least 4. We also have 1 squaring, but a squaring of a variable in hardware is about half as costly as a partial multiplication. We also have the gadget for the 2-piney gadget with 3 shares. And it uses 6 multiplications. So what did I do? Thanks. Which uses 6 multiplications. The ×2 operation here, it's just a rotation of the bits in a Mersenne prime field, so it costs us nothing. And otherwise, I have additions and subtractions of the randomness. Now this is the one for 3-piney, so 4 gadgets. Now the interesting part is these 2, they work in 1 cycle, so technically in 2 cycles, but 1 register stage. So we typically say a single cycle gadget. This one also a single cycle gadget. This one is a 2-cycle gadget. And here is our arbitrary order algorithm for obtaining a D-1 piney squaring gadget for any field. This one also needs 2 cycles. So the 1-cycle versions for 2 and 3 shares, they're actually optimized versions of this algorithm. Now to compare multiplications with the squarings that we just presented, we compare to HPC1 because that's the piney multiplication, and we also have a piney squaring gadget here. What we can see is that the multiplication for HPC1, the partial multiplications are d squared, while in our case, it's just d times d plus 1, half minus 1, and 1 squaring. So it's asymptotically about half as expensive as using a multiplication gadget. On the randomness side, however, it's very similar. Using these gadgets, we have now obtained like a number of order-specific piney AES prime S-boxes. So masking this x to the 5 plus 2 operations. For 2 shares, we have twice the single cycle squaring gadgets, then a DOM INDEP multiplication to achieve a 3-cycle masked S-box. For 3 shares, we need an extra register between the second squaring and the DOM INDEP multiplication. And for 4 shares and all further orders, so from there on it's generic, we need 5 cycles for the masked S-box. The constructions and the proofs for these constructions are found in the paper. Now, this is just a slide to say implementing addition and multiplication followed by a modulo reduction is not like super complex in hardware. So we have like VHDL code for field addition and field multiplication in arbitrary Mersenne prime fields. You can just take this code and it works for any field, and it synthesizes to something pretty efficient. What we have then in the comparison is we compare the standard AES box masked using the HPC2 masking scheme and the Boyer-Peralta representation of the S-box in 6 cycles versus our AES prime S-box, which these order-specific constructions. And what we see is that the overhead for the unmasked one is quite significant. So we are more or less than 3 times larger, but the overhead for like the masked variants is significantly lower, sometimes only 30%. And they can still be clocked more than 400 megahertz in this technology and use fewer cycles. Actually, if you don't need this high frequency operation and you are also happy with like 100 megahertz operation, the area is actually very similar between the AES and the AES prime S-box, and the randomness is also pretty equal. Now, the same on FPGAs. This is like a slightly different case because on most FPGAs, we have DSP slices. And DSP slices we can use for arithmetic multiplication. So they are there. We have arithmetic multipliers and can use them for our implementation. And the middle area of the table, it shows exactly that when I use these. So here we have the DSPs that I used, the multipliers. And then the area in, or like the resource utilization on the FPGA is actually quite similar between the AES and the AES prime. If we prohibit the use of these DSP multipliers, then the AES prime is almost twice as expensive. Now here are some side channel evaluations of those 2 S-boxes. On the left side, we have the AES S-box masked with 3 shares. On the right side, we have the AES prime S-box masked with 3 shares. On the top, we have sample traces. Then below that, we have the SNR values of the individual shares. So this is important because the SNR values on average between those shares is actually quite similar. So it's not that in the prime masking case, we just leak less because we have different kinds of operations. We leak about the same for each share, and we still get much better security because the share combination doesn't have this algebraic compatibility with our leakage functions. And below that, we see like t-statistics, 3rd order, and below that, the result of a profiled Saska attack, where we plot the key rank over the number of traces. And we can see that in the binary case, so in the AES case, we succeed with the attack, while in the prime case, we don't. Now, if you've seen me present at CHES before, you probably heard something about static power attacks. This is like a low noise attack against hardware implementations where you stop the entire circuit. Then you measure the current that's still flowing while there's no operation, while there's an idle state. And then from that DC current that you measure during that time, you can infer some information about the state of the circuit that is saved. And you can do that for like an arbitrarily long time because it's not a momentary effect, it's a static effect. So you can often reduce the noise a lot, which is like very relevant to our masking comparison. And this bottom figure is just to show we didn't use like a climate chamber in this experiment for like availability reasons, but instead corrected for temperature variations with a moving average filter. Using this, so like the top 2 rows are for 3 shares, while the bottom 2 rows are for 4 share implementations. So with the static power attacks, even using like 10 times less traces, we actually can attack 1 order more for both of those implementations for the AES S-box and the AES prime S-box. And we can see that we have like more than an order of magnitude advantage in the security. Here is like a table comparing the data complexity, so the number of traces that we need for an attack. And yeah, they are separated between AES and AES prime and dynamic power and static power. And then we can see what the factor is between these attacks. And in the best case, we have a factor of 75 times more traces that we need for a successful attack on the AES prime compared to the AES, which I think is pretty impressive for like the overheads that we have to spend. Now the conclusion, in our opinion, additive masking in small and implementation-friendly prime fields seems quite promising for physically secure cryptography, because we can mask securely without the need to guarantee a notable amount of noise, which goes very much in the direction of minimal assumptions. Then we have built like secure and composable squaring gadgets to enable hardware designs which do this efficiently. What we demonstrated is that the security advantages can be multiple orders of magnitude, really. And what we need to explore this design space further is actually ciphers, which are much more efficient than this AES prime toy cipher that we used in this experiment. Our code for the prime field masking examples is public in the GitHub. The link is given. Yeah, that's all from my side. The only thing that I still want to say is that if somebody finds that interesting, we have open positions in this field of research at UC Louvain in Belgium, both for PhDs and postdocs, as far as I know. So let us know if you're interested.
Thank you. Any questions from the audience? Yes, a few already. Here one and here one.
Thank you for the presentation. About the first slides that you presented, how your observations are extending to other leakage function, for instance, linear ones with real valued coefficients.
I didn't get that acoustically.
Excuse me. So you for the first slides you are presenting observations for the Hemingways.
Yes.
And my question is, how do those observations extend to other leakage functions? For instance, first with linear leakage functions with real valued coefficients.
Yes, I mean, like the simple examples where you just count and list the probabilities, they're not so much. But like with the probability distributions, you still have that. I mean, that's what these information theoretic plots show, right? Here's the noise is actually like not discrete. And for linear combinations of the bits, you have the same behavior. There are, of course, leakage models where also Boolean masking without any noise gives you security amplification. But the more important part is there are no leakage models which are non-injective that don't give you security amplification for the prime field.
Okay. Okay. So thank you.
There was another question here.
So thanks for the nice talk. If I want to use the prime field masking for AES, for example, there is any efficient way to implement the linear functions over prime field masking, or I have to get back to Boolean masking?
There is no efficient way to apply this to a standard binary cipher. So you really need to have cryptographic primitives which work in a prime field.
Okay, in case of the mixed column of AES, for example, how you make it, for example, first order or second order secure in prime field?
You don't.
Oh.
I mean, that's the thing, right? You wouldn't want to do that. If you have AES, like the standard AES, you would use Boolean masking because it's like adapted to the representation of the cipher. What we propose is to have new ciphers which are adapted to the representation of the prime field. and then we can effectively protect them. That's why we have built this toy AES, which is for
I
prime
see.
field, so that we can actually apply it.
Okay.
Otherwise, I mean, there are surely methods where you can first do a conversion into the prime field, then mask in prime field, then do the conversion back, but that will be like super inefficient. So you wouldn't want to do that.
Thank you. Thank you.
Any other questions from the audience? Just a quick question from me. It's very it's much more efficient when you do mask implementations, but for unprotected AES, the new AES is way less efficient, right? Do you have ideas how this can be improved, or it's not possible to be improved? Because usually you need also to have unprotected version also efficient, right? I mean.
Yes, indeed. So what we experienced when like building prime field designs is that you have the largest overhead for the unprotected implementations. And I mean, if you design a cipher for a prime field operation, you would design it completely differently than the AES, but you probably still do not get close to like the efficiency of binary ciphers when unprotected. Our goal is more to get close to the efficiency when protected, because only then we also have the security advantages. Otherwise, we don't have them.
Okay, thank you. No questions from the chat. Let's thank the speaker again. Okay, we have the second speaker ready. We just wait for the slides. Coming, I hope. Loading, okay. Okay, so we have the second paper, which will be on low latency and low randomness second-order mask cubic functions, and Ian will present it.
Thanks for the nice introduction. So in this paper, as the name suggests, we try to reduce the latency of cubic functions, second-order mask realization while keeping the randomness cost low. But let me start with the problem we have. So we know if an attacker can monitor the physical properties of a target device, such as power consumption or electromagnetic radiation, then he can gain information about the secret. So the solution our community came up with is trying to mask our secrets. So masking schemes are based on secret sharing, and it tries to randomize sensitive data during the execution of the cipher to reduce the dependency between the secret and, of course, the physical property of a target device. And one of the most popular approaches is Boolean masking. So in this context, if you want to share a sensitive value X into two shares, namely X0 and X1, we need a single bit of fresh randomness R. And the first share is actually the randomness, and the second share is X XOR R. And to calculate back the unshared value, we need to XOR the two shares. So in this way, the adversary must recombine the shares to gain information about the sensitive value, making it hard for attackers to mount a successful attack. So to verify the security of a given design, multiple security models have been introduced. One of the first models is actually probing model. In this context, an adversary can probe up to D probes or D signals or D intermediate values. And if any set of D probes is independent of the secret, then we assume the given design is disorder secure, and it can prevent disorder side channel attacks. However, it has been shown that this model doesn't reflect the reality in hardware platforms, and basically it doesn't cover the physical defaults such as glitches. So to cover that, a glitch extended probing model has been introduced. And in this model, a probe propagates backwards up to last synchronization point, which is usually a register layer, or a primary input. So to show the difference between these models, I brought a very simple example here. So here, in traditional probing model, if we place a probe on a signal, then we gain information about exact value of the signal. However, in glitch extended probing model, we gain information about all inputs that are involved in the calculation of the probe signal. So it has a much more higher information. The attacker has more higher information, and it is a much more stronger security model. And we consider this because we are dealing with hardware platforms in this paper. So one of the first strategies, which is secure under glitch extended probing model, is actually threshold implementation with three well-known properties, namely correctness, non-completeness, and uniformity. And it defines the number of input shares based on the algebraic degree of a target function, which is shown by T, and the desired security order D. So for a cubic function, we need at least 7 input shares to achieve second order security. There are another line of strategy that use the minimum number of input shares, namely D+1 shares to achieve D order security. And here are brought very simple example of 2-input AND gate, which is first order secure. And you can see the general structure of the circuit here. So, oops. Yeah, so here you can see basically the circuit, and the general the structure is divided into 2 parts by a register layer. The first part is the expansion layer, which consists of multiple coordinate functions, and then we have compression layer to generate the output shares. So in this paper, we try to create a second order masked version of 4-bit cubic functions. And to do that, we follow 3 steps. We first find a correct and uniform sharing, and then we achieve first order security with no fresh randomness. And we add fresh randomness to achieve second order security. And we use only 3 shares, which is the minimum number of input shares, because we want second order security. So I try to explain this step using a very simple example here. So we have A, B, C, and D, which are the input bits, and then X, which is the output bit. And first we want to have second order non-completeness in our coordinate functions. This means that for each input variable, only 1 share should be given to the coordinate function. So in a naive way, we need, because it's a cubic function and we have 4 input bits, we need 81 coordinate functions. But because it's nature and because it's cubic, we need only 27 coordinate functions. And there's a nice paper that actually proves the optimality of this number. So if I list the index shares in a list or in a table, then we would have something like this. So basically, this table shows for each coordinate function which input shares should be given to the coordinate function. So for example, the first row shows A0, B0, C0, and D0 should be given to the coordinate function number 0, and the other coordinate function also shown in the table. I also, you can see I divided the coordinate function into 3 groups using the dashed line, and it means that these groups are going to the compression layer later on to generate the output shares. It is important to note that, for example, here, the first, let's see if it works. Okay, so the first column I assign to the A, and the second column I want to the B, but this is not the only possibility. We can, of course, switch that, and I can assign, I don't know, I2 to A, or I3 to A, and so on. So we have 24 different index configuration table based on how I assign it. And it is important to consider all of them to receive or find a solution for a given design or given function. So once we select an index configuration table or one of these assignments, then the placement of cubic shared monomial is actually fixed and it's already clear. So in case of our simple example, for example, A0, B0, C0 should be placed in coordinate function number 0, and A1, B1, C1 should be placed in coordinate function number 14, and there are no other possibilities based on this table. But we have freedom actually in placement of the linear terms and quadratic terms. But at this point of paper, we just need a correct sharing. So we just choose one of the possibilities and we move on to the next steps. So here I fixed basically the index configuration table, and to try and to find a uniform sharing, we try to add correction terms. And we just consider linear terms, because if we add quadratic terms here, then the search space would be too large and we cannot search the entire search space using a computer program. So getting back to our simple example and considering x0, x1, and x2 as the output shares, then we have 4 possibilities for each correction term z. So we can add it to the first 2 shares, we can add it to the first and the last shares, and we can add it to the 2 last shares, and of course we can add it to none of them. So we have 4 possibilities, and for this configuration table, we have 9 possibilities that I wrote here. And then the search space would be 4 to the power of 9. And that's why actually we just consider linear terms, because as you can see, the search space grows exponentially. At some point, it is not feasible really to search the entire search space. So here is an example of a correct and also uniform sharing of our target function or of our simple example, but it's not necessarily a first order design. So to show why, let's suppose that we probe the x0 here, which is one of the output shares, and it propagates under glitch extended probing model to all these coordinate functions. So actually just using these 3 probes, we can gain information about the unshared value C. So to make it first order secure with no fresh randomness or no additional fresh randomness, we try to pair 2 S boxes. So let's consider S1 and S2, which are 2 S boxes, and X bar is the input of S1 and Y bar is the input of S2. And it is really important to note that X bar and Y bar are independent of each other, which is a fundamental assumption in any masking scheme, that the plain text and the key are shared uniformly and each bits of them are totally independent of each other. So if I represent the bits of X bar with A, B, C, D, and Y bar with K, L, M, and N, then we can pair S boxes like this to achieve first order security. So as you can see here in the first group, yes, here I added K0 twice, L0 twice, M0 twice, and so on. This means that in the subsequent compression layer, the added terms are canceled out. So it doesn't have any impact on the uniformity of the sharing. And you can see the way we added in this group is also similar here and here. But the design is not second order secure as well. So to show why, let's suppose that we probe the first output share x0 and it propagates backward to all these coordinate functions. And with this set of probes, we can gain some information about the added terms in green. And with the second probe on x1, then we have another set of probe on these coordinate functions. And actually using these 3 together with these 9 probes, then we have a leakage about the input variable C. So to make it second order secure, we use fresh randomness. So we take R0 and R1, which are totally independent of each other and different, and add it in a circular way, which is commonly known in our community. So the good thing here, because the design is already first order secure with no fresh randomness, and we just use fresh randomness to achieve second order security, then we can reuse these randomness. So we call them static randomness because they can given to the encryption function at the start of the encryption, and they do not need to be updated every clock cycle, and they stay unchanged during the execution of the cipher. So this is the static randomness, we call them in this way. Note that if they are the traditional way of fresh randomness that are updated every clock cycle, and the design is not first order secure without them, then we cannot reuse it. To show you why and give you an intuition why we can reuse the fresh randomness, let's suppose that we have 2 pairs in a round function, the same round actually, and we put 2 probes in 2 different pairs. So with the first probe, we can gain some information about some shares of X bar and some shares of Y bar, and of course, some bits of R0. And with the second probe, we can gain information about some shares of P bar and some shares of Q bar. So again, P bar and Q bar are independent of each other, and they are independent of X bar and Y bar, meaning that the information that we gain by probing the first pair is not actually useful to gain any information about the secret. And the entire structure of a pair is actually first order secure, even the entire R0 is fully known. So it means it is second order secure and there is no information leakage when we probe two different pairs in the same round. However, if the two pairs are in two different rounds, then there might be a leakage. And to avoid that, we use dynamic fresh randomness. It means that they are used to make two probes in two different rounds, totally independent of each other. And these randomness should be updated, that we call dynamic randomness. They should be updated every round. So to explain it a bit more, let's have a look at the case study. Midori's box was later also used in Craft and Monty's and other block ciphers. Has 3 cubic functions and 1 quadratic one. And of course, for quadratic one, we need fewer coordinate functions. We found millions of uniform solutions for each of these functions. And then we wrote another program to find a joint uniform solution because we are interested in a uniform sharing of the Midori's box. Then we followed the steps and we paired two boxes to achieve first order security while using no fresh randomness, and we add fresh randomness to achieve second order security. We checked the designs and verified the security of them using ProLead and Silver, which are verification tools. So the general structure of Midori is like this. So you can see we have a S-box here. It just needs a static randomness. And as I said, they stay constant during the execution of the cipher. We need just 2 layers of register, and then we have a compression layer to generate the output shares. And here is the dynamic randomness that we add into the mix column. So the reason behind the dynamic randomness, as I said, to make the probes independent of each other if the attacker put probes in 2 different rounds. And note that the number of dynamic randomness is way less than the static randomness, and that's why we cannot use the dynamic one instead of the static randomness. So we applied our technique to 3 case studies. So the first one is actually Midori, and you can see we reduced the latency to 32 clock cycles at the cost of course, fresh randomness, but it is not the way that we use fresh randomness, which updated every clock cycles. That's why it's not actually skyrocketed. The same holds actually for the next case study, which is Skinny. It has 64 clock cycles latency, which is better than the state of the art at the cost of a bit of more fresh randomness. For Prince, our design has 24 clock cycles, and the latency is actually 24 clock cycle here, but actually we have another design that offers the same latency, but if you look at the fresh randomness here, it needs at least 34 times more fresh randomness. So here in this paper, we reduce the number of fresh mass needed to perform a second order encryption quite significantly. So to sum it up, we introduced a technique to create a second order masked version of cubic function with low randomness cost. We applied the methodology to several block ciphers, including Midori, Skinny, and Prince, and we confirmed the security of our design with 2 verification tools, namely Silver and ProLead, and we verified the security of our designs using experimental analysis. Thank you so much, and I'm happy to take any questions.
Thank you. We have plenty of time for questions. Thank you. So we have 5 minutes. If you have any questions, please raise your hand. We will More questions?
I don't know if it's good or bad, but hopefully I explain everything well.
See if there's anything from the chat, no? Maybe I can start and then
Okay.
maybe more will come. So for low latency, low latency ciphers in general, masking seems to be a bit of too expensive. Do you think there is any way to improve that, or we should look at something else for protecting low latency?
Yeah, definitely.
ciphers?
There is a lot of room for improvements to achieve low latency. Maybe one way is to generate the phrase randomness with a very low cost. In hardware, it is also an open problem how to generate it very efficiently sometimes. This is one way to go. Another way, what we have done to reduce the need of phrase randomness using in a way that the algorithm suggests to reuse the randomness. But of course, there are a lot of improvements, and hopefully we can get better over time.
Thank you. Any more questions? Yes.
So in your approach, you use the static randomness within the S box, right? And you reuse them for the entire within the round, and you have the dynamic randomness in the mixed column, right?
Yes.
Do you save any randomness by shifting the dynamic randomness from the S box to the mixed column? Because otherwise you wouldn't need the dynamic randomness in the mixed column, right? So if you do the dynamic randomness in the S box, is this more expensive?
I mean, for example, in case of Midori, we are talking about 200 static randomness and only 32-bit of dynamic randomness. So you cannot use them for the static one. I mean, there are not enough randomness actually.
Okay. Yeah.
So,
Thanks.
yeah.
More questions? If not, let's thank the speaker yet again. And we move to the last talk for this session.
It's getting ready.
Yeah, we'll fix it. No worries. Can you reset the clock and put the slides, or? Okay.
Good.
Okay. Here we are. So we have Srinivas Vivek, who will talk about a faster territorial masking of lookup tables.
Yeah. Thank you. So this is a joint with my students, Anju Alexander and Annapurna Velivati. Yeah, so I have some basic slides. I'll just quickly run through them for the sake of completeness. We all know that side channel attacks are important, right? And crypto implementations need, algorithms need secure implementations, right? And masking is a very popular countermeasure. So if we have a teeth order on a teeth order secure masking, we need T+1 shares, where all but one shares are randomly and independently chosen, right? And then we also know that the attack complexity increases exponentially with the number of shares. So in this work, we focus on masking of S boxes. So if we take typically in a block cipher, we say, for instance, AES has this 4 set of operations, all but the S box masking, they're all linear operations, and it just needs a linear amount of time to mask these linear operations, while it needs a quadratic amount of operations in the number of shares to mask linear operations, right? And of course, we need a leakage model to formally argue with security, and a very popular leakage model is the probing leakage model, right? And then, so we need to design a compiler that transforms the original circuit into a probing resistant circuit where it still the secret remains secured, even if adversary probes T number of shares, right? Typically, the countermeasures or the masking schemes for the S boxes can be classified into two types: circuit-based masking. So we have the popular ISW masking and many follow-up works, and we also have the table-based masking, right? Where mainly the S box, they all differ in the fact that S box is either represented as a Boolean arithmetic circuit in the case of circuit-based masking, or is it represented as a temporary lookup table in the case of table-based masking, and I'll abbreviate it as TBM. So the basic idea of the table-based schemes is to construct a temporary lookup table in the RAM. Okay? And typically this is done as part of the pre-processing or the offline phase, where we do not need all the shares. I mean, the very final shares, and the fact that the rest of the shares, they can all be pre-sampled. So this phase is typically the pre-processing phase, where we shift the table, right, with all but one share. And in the final phase, the online phase, we need the final share, and we do securely look up the shifted table. So all the table-based mask schemes are basically designed on this principle. And oh, sorry, I think I should. And so far, until very recently, only table-based mask schemes supported pre-processing, and they had very, very fast online phase until the works of Wang et al. From the CHES last year, and also the very first talk in the previous session, where we can get like pretty impressive timings with pre-processing, even in the case of circuit-based masking schemes. So the very first countermeasure that was like formally proven to be secure was from Crypto 99 by Chari and others. So basically, as I mentioned, it's this table-based masking scheme works by shifting a table. In the case of first order masking, we just need to do one shift of the S box, right? And then mask it with an output mask. And the online phase is simply looking into the table with the second mask. So then we get two output shares, right? And then the second order table-based masking scheme was proposed by Riva, Dotax, and Proof from FSC 2008. And of course, it also only has a single shift and only a single temporary table, right? But it was, it works only for S boxes. Means not any arbitrary function S, but S boxes means the particular property we need is they need to be balanced. Means every element in the codomain should have equal number of pre-images, right? So basically, their scheme works simply by choosing one extra random variable. Of course, we need to sample the output shares and doing only one shift, right? With the input shares x1, x2, which can be pre-sampled, and d, which can be pre-computed, and also is v, right? And then the final offline phase is simply looking up the table with the third share, right? And then there were many table-based masking schemes proposed, but they were all broken, mainly by Coron and others. And the next scheme was table-based masking scheme that works for arbitrary order by John Sebastian Coron from Eurocrypt 2014 and Coron others from CHES 2018. Again, the number of shifts that are needed are proportional to the number of shares. Means we need to shift the table with every input share, and then we need to refresh every row of the table. So consequently, amount of randomness is proportional, is quadratic in the number of shares and also the size of the table, and also amount of RAM memory is also needed. It's proportional to the I would say it's 2 power n is for an n to n bit S box, it's 2 power n, that many rows will be there, and we need t number of columns, or t plus 1 number of columns, okay? And m is the size of the word. So and in general, it's very, but it works for any S box. So in general, this table-based, particularly higher order table-based masking scheme, in spite of a couple of improvements over the previous years, still need a lot of memory, right? And then randomness, and then total execution time. Okay? But again, the online time is still like very fast compared to circuit-based schemes. So our motivation, in fact, partly inspired from the multi-party computation community, where there are many numerous works, that propose customized protocols for say 3 number of parties or 4, 5, and so on. So we realized that in the case of, as I also mentioned, in the case of table-based masking schemes, we have customized masking schemes for first and second order, and then we have for third order we need like an instantiation of an arbitrary order masking scheme. So our idea is to propose customized third order masking scheme, hoping that it's like more efficient. Right. Yeah. And also now we are equipped with formal security notions. So yeah, our hope was to still we'll be able to argue the security. Right. Of course. So I mean, straightforward extensions to the scheme of Riva and others from FSC 2008 doesn't work. I mean, I won't get into details, but there will be a third order attack. So we need to explore many tweaks. In fact, in the appendix of our paper, we have listed possible ways things can go wrong. So just for the sake of completeness, and then yeah, finally we are able to propose a scheme that is 3NI secure, supports pre-processing. Okay. And then, of course, it's more efficient. Roughly, it will be 5 times. The total execution time will be 5 times faster than the higher order scheme instantiated at the third order. Okay, our scheme consists of 2 procedures. Okay, offline and then the online phase. We just do 2 shifts with the temporary table. Okay, and then the online phase, I'll get into the details, but the main component is the customized third order secure, SNI secure, 3 SNI secure refresh gadget from Bharat et al. Right? So it's quite efficient. And then we see that we just need the, like 4 randoms, right? Okay, yeah, we just need, yeah, 4 mini randoms. And then, so this turns out to be 3 SNI, right? And it's pretty useful. So our algorithm works like this. We initialize the table with the S box, okay, generate the 3 input shares that can be sampled independently of the 4th share or independent of the secret. So generate 2 output shares and then a random vector, because if we don't choose a random vector for like 2 power n many vector y, that's going to be our 3rd share. If it is not a vector, instead of a single value word, then it will be prone to the classical attack where if we XOR the 2 rows of the table, then it will be insecure. So shift. So as I mentioned, we shift the table 2 times because we have 4 shares. The typical higher order mask table-based masking algorithm instantiated a 3rd order would need 3 shifts, but we could still do with 2 shifts, and we don't need to importantly refresh every row of the temporary table every time we shift. Okay, unlike done in the arbitrary order case. So, and then the 3rd share is simply, yeah, the vector looked up with the 4th share. Of course, sorry, yeah. Yeah, that will be the part of the 4th share. Using 4th share, we are going to look up the 3rd share, and then the final table lookup will give us the 4th share. Yeah. So, and then what you see in the green is the online phase, and we see that it's quite intuitively, it's going to be pretty quick. So, how do we prove the security of our algorithm? So the key thing is offline phase is independent of the secret. So, and then the final table only requires the 4th input share. So in fact, we show that the offline phase is 3NI secure. And then the fact that the refresh gadget is SNI secure and there's only 1 input, oops. So then the whole thing turns out to be 3NI secure. Okay, yeah. So that's what is represented diagrammatically. okay, we perform just for the sake of benchmarking, we run our experiments on an ARM Cortex M4 microcontroller that comes with an inbuilt RNG. So we get an approximate 2-factor reduction in the NAND memory usage because we don't need a replica of the table as in the case of the higher order scheme. So we just need one table, and then our online execution time is about 8 times faster than bit sliced masking of AES-128 at third order. And the total running time compared to the instantiation of higher order table-based masking at third order, it's about 5 times faster. Okay. Yeah, so here's the table where we compare the memory required, randomness usage, and the total time that's split into online time and offline time. So you see the first row, like the first row is for our scheme, and then this is the increasing share variant of the higher order masking scheme from CHES 2018 instantiated at third order, right? And then this one with the large register variant. Okay, and then the final row is for the present cipher. So we achieve like pretty fast online time. That's on par with what is already known. And as you can see, the total time is like, we need about 3.9 million clock cycles, right? So now compared to 36 or 18, right? So we are pretty, like fast. And then, of course, for completeness, we also compare with the circuit-based masking schemes, so that have pretty high for using the river-proof thing from method from masking of AES from CHES 10. So it's 0.9, and then using bit slicing, it's 0.84. So, but again, the paper from Wang and others from the last year CHES, and also what we saw in the first session, like pretty impressive. So our online time is comparable, but then offline time is like pretty fast. So it will be pretty interesting maybe to adapt the techniques of Wang and others in the case of table-based masking schemes. Right. So we proposed, just to conclude, or probably that was like pretty quick. We proposed a third order table-based masking scheme that's 3SNI secure. And then, so thanks to now we have formal composition notions. So our attempt was, I think, I would say successful, at least improving the security. Unlike 2 decades ago where these schemes got broken, right? But we are not able to, because there are no tools to directly verify the security of compositional security of table-based masking schemes. So we could not, formally verify, but we have given mathematical proofs in the paper. So we could explore doing the same thing for like slightly higher orders, come up with customized schemes that are like much more efficient, right? So that's it, I would say. Thank you for the attention.
Thank you.
Be happy to answer any question.
And we have plenty of time for questions. Yes. Yeah, we have Mike here.
Oh, by the way, we have as part of artifact, we have also provided the code that we have used for the implementation. I hope that's not the question you have asked.
Thanks for the talk. I was wondering whether you would consider also proofs in the random probing model. What would that give for a table-based masking?
That's pretty interesting. We did not explore that, so I'm not able to answer that right away.
Questions? Yes.
Just a small question. Did you do any practical evaluation? Like t-test?
No, we could not do that. But anyway, I mean, I should confess that our implementation is not hardened against side channel attacks. Our main purpose was to provide, some benchmark for the timings. But anyway, the code is available publicly. If anyone interested could attempt an evaluation.
Thank you.
Any more questions? There is no questions from the Zoom, so I guess everybody wants to get to lunch. So thanks everybody in the session.